Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we are going to be augmenting our understanding of different kinds of areas associated to curves or curve segments. We're going to introduce two special kinds of areas called slices and caps, and then we're going to connect that with the classical formula of Archimedes relating to the area of a parabolic slice. Okay, so far what we have is a curve and a curve segment, say gamma there, going from T to U. And associated to this segment of the curve, we have the principal signed area. The signed area from T to U of gamma, which is the region formed by this curve and these two lines emanating from the origin. So this quantity here, which is the primary quantity that we're studying, is really this sort of wedge-like area that we're defining from the origin. But we also have seen that there's some associated areas that we call the signed x and signed y areas. For example, Sx, it's a signed x area associated to the curve. That's, in this case, the area underneath the curve to the x-axis. And similarly, we have the signed y area of the segment, which is the area between the segment and the y-axis. So that one is in red, this one here is in green, and this one here is in black. So we have a segment of a curve, and associated to it we have so far three signed areas that we can deal with. Now, in today's lecture, we want to introduce two more variants, which are called slices and caps. So here's that same segment of the curve gamma from A to B. And we're going to define the area, the signed area of this green region here, which is obtained by slicing the curve with this chord from A to B. So it's the region determined by the curve and then just a straight segment connecting the two endpoints of the curve. So we're going to call that region a slice, and its signed area is going to be denoted by SS, so signed slice area from T to U of gamma. And the other variant is going to be called a cap. So what is a cap? Well, a cap is this region right here, bounded by two tangents, tangent at A and the tangent at B, with the curve. So these two tangents meet at some external point, let's call it X. And so this region here will be called the cap, and the signed cap area will be denoted this way, SC from T to U of gamma. So we're interested in getting hold of what these things are and being able to evaluate them. So let me remind you that a polynomially parametrized curve, or a Casteljau Bezier curve, they're essentially the same, is an expression of the form gamma equals PQ in brackets, where P and Q are polynumbers. And a segment of such a curve is an expression gamma sub T super U, where T and U are rational numbers. Now the fundamental theorem gives the signed area of such a segment, and we have a couple of different notations for it. So the signed area from T to U of gamma, or the signed area of the segment gamma from T to U. And we've seen that the fundamental formula for that is that that's 1/2 the Faulhaber integral from T to U of the area differential d of gamma. And that is the polynumber P dq minus Q dp, where d is the Faulhaber derivative. Okay, and I also remind you that the signed x area can be written this way, Sx from T to U of gamma. It's the Faulhaber integral from T to U of Q dp, sort of half of this. And the signed y area is the other half, Sy from T to U of gamma is Faulhaber integral from T to U of P dq. Okay, so those are the signed areas that we already have. Now we can get some motivation for the slicing process by thinking back to our discussion of polygonal splines. So for example, suppose we have an oriented polygonal spline A1, A2, A3, A4, as in this diagram. A1, A2, A3, A4. So we're talking about this little spline there. Then I remind you that the signed area of such an oriented polygonal spline is the sum of the signed areas of its constituent oriented edges. So that'd be A1, A2, signed area of that, plus the signed area of A2, A3, plus the signed area of A3, A4. And what this is geometrically is what we think about in terms of the area, the oriented area of this polygon formed by the spline and the origin. And it contains the signed area of this thing, and then the signed area of the second one, and then the signed area of the final triangle. Now, if we go to the cyclic oriented polygonal spline, denoted with this double arrow over A1, A2, A3, A4, it means that we're augmenting the edges that we have with a fourth edge going from A4 to A1. Okay? So that's now a picture of the cyclic oriented polygonal spline, A1, A2, A3, A4 with a double arrow. And the signed area of this thing was equal to the signed area of the original one, namely what we already had in red, plus the signed area of A4, A1. In other words, the signed area of this new edge that we've added. And the effect of that is to basically nullify the contribution of this triangular portion. So what remains is just this area here. Okay, so that's a closed region as opposed to a sort of an open region to start with. Okay, so that's our motivation for this definition. For a polynomially parametrized curve gamma, the signed slice area of gamma from t to u is, so here's the picture, let's have a look at that. So here's a curve, and there's a segment of a curve from here to here. From A, which is gamma of t, all the way up to B, which is gamma of u. What we want to get at is the region formed by slicing off a portion of the curve. We just cut from A to B. And then this region here is what we want to get at. So how are we going to get at that? Well, it's very similar to what we did here. We're going to define the signed slice area from t to u of gamma, and alternate notation, slice sine area of the segment gamma from t to u. The definition will be the signed area from t to u of gamma, which is the original area emanating from the origin, plus the signed area from B to A. In other words, this oriented edge from B to A. The effect of that is we're taking the area of this sort of wedge emanating from the origin and subtracting the signed area of this triangle here. So this intermediate region sort of cancel, and we're just left with this region bounded by the curve and the straight segment from B to A. And A here, as we've seen, gamma of t, and B is gamma of u. These are the endpoints of the curve. Okay, so this is a definition of a signed slice of a curve. What we get when we take a curve and we draw a line slicing the curve and creating a region thereby between the slicing line and the original curve. The area of such a slice is actually historically a very natural thing to consider, because that's exactly what Archimedes was looking at with his famous parabolic area formula, where we have a parabola, we have 2 points on the parabola, and we're slicing off a certain region by taking the chord between those 2 points on the parabola and essentially slicing it along that chord. So I remind you that his famous formula gives us a way of obtaining the signed area of such a portion or slice of a parabola. Now for us, the simplest case is when the parabola is represented by a quadratic function. So in classical courses, we would write y equals, say, b0 plus b1x plus b2x squared in terms of x and y coordinates. But we'll prefer to write it as the curve gamma given parametrically by alpha and b0 plus b1 alpha plus b2 alpha squared. And we're going to consider the segment of that curve going from some number t to some number u, as represented here. So maybe there's a, which is gamma of t, and here's b, which is gamma of u. So we're looking at that portion of the curve, that segment. Okay, so, well, we know how to get such a signed area just of this segment. The traditional signed area of it is 1/2 Faulhaber integral from t to u of the differential of the curve. And not too hard to work out what the differential is. This times the derivative of that minus this times the derivative of that. It turns out to be minus b0 plus b2 alpha squared. And we can integrate that easily enough, and we get minus b0 over 2 times u minus t plus b2 over 6 times u cubed minus t cubed. So that's the traditional signed area of that segment. Now what about the oriented edge from B to A? Well, that's pretty easy because we're just talking about the 2 points, and we know exactly what the formula for those 2 points is. So we just apply the elementary formula for the signed area of an oriented edge to get 1/2 of b0 minus b2 times tu times quantity u minus t. That's a small calculation involving essentially the cross product of 2 vectors. Okay, now we have the ingredients for the signed slice area of this curve. The signed slice area from t to u of gamma, which is exactly what's represented here in this picture, is by definition the signed area of the curve gamma from t to u plus the signed area of the oriented edge BA. Okay, so we have to take this quantity here, and we have to take this quantity here, and just add them. And you can perhaps see that there's some nice cancellation here. The b0 to u minus t terms will cancel, and then there'll be some additional terms that will combine with that. And pleasantly, we just get 1/6 times b2 times u minus t cubed. This is a very nice formula. It's very elegant, it's very compact, and interestingly perhaps, it doesn't depend on b0 or b1. It only depends on b2. And it depends on u and t in a nice way. It's just the difference cubed. So this is some kind of indication that this is actually a quite nice quantity. It's arguably simpler than the 2 ingredients that make it up. But it's also an important stepping stone to understanding why Archimedes' formula works in this situation. All right, so the other ingredient that we need to set up Archimedes' formula is a 3rd point on the curve. And that's obtained by taking the segment that we're interested in, and its endpoints A, B, and taking the midpoint of that side. There it is there. And then it turns out that we draw a line through that midpoint, which is parallel to the axis of the parabola. Or in projective terms, what you do is you connect this point with the unique point at infinity on the curve. So the parabola is determined by the fact that it's sort of tangent to the line at infinity. It meets it at just a single unique point. And so that's actually the direction of this axis direction that goes through M. And where this meets the curve at the 2nd point is the point C. Now it turns out, one can relatively easily check, that this point C is also characterized by the fact that its tangent is parallel to AB. But actually it's better to think about it the first way I described, that it's obtained by this line from the point at infinity to M. There's another characterization of C. It's the point on here for which this inscribed triangle ABC has maximal area. But again, that's not the best way of thinking about it. The best way of thinking about it is through this point at infinity construction. Okay, so we can get at this point C relatively simply because it's just a question of taking 2 points and finding their join and then seeing where that line meets the curve. So A is the point gamma of t, so there's its coordinates there. Here is B, that's gamma of u, coordinates there, and not hard to check that this point C is given this way. Its x-coordinate is t plus u over 2. That's kind of obvious because this is actually a vertical line. And then here is the y-coordinate, b0 plus b1 times t plus u over 2 plus b2 times t plus u over 2 squared. So it's just gamma of t plus u over 2. Now, if we have 3 general points, gamma of t, gamma of v, and gamma of u, then the signed area of that triangle, ACB, the oriented triangle, is 1/2 of the determinant of this 3 by 3 matrix. That's another way of expressing the signed area of an oriented triangle. And when we work this out, it's a nice sort of alternating expression in t, v, and u. It's 1/2 of b2 times u minus t times v minus t times u minus v. And then when we take this general equation and replace v with the actual relevant value for point C, which is t plus u over 2, then this simplifies and we get that the signed area of ACB, this one right here, is 1/8 b2 times u minus t cubed. Well, the previous one, the signed slice area, was 1/6 b2 times u minus t cubed. So we can immediately deduce Archimedes' parabolic area formula, which is that the signed slice area is 4/3 the signed area of the inscribed triangle ACB. This is very, very historically important formula because it's really the first calculation in calculus. It's definitely a calculus calculation, and it establishes that a slice of a parabola is actually something that we can get at. There's actually a rational number associated to that area. And we can get at that rational number by calculating the area of this particular triangle, which is a purely rational thing, and then simply multiplying by the factor 4/3. This is beautiful. And Archimedes recognized that this was a very special property of the parabola, not shared by the circle or the hyperbola. Okay, you can't do something like this for a circle or for a hyperbola. Just in the parabolic case do we have such a beautiful relationship. Now, in a classical calculus course, one could do something like the calculation I've just made, and therefore say that, okay, we've proven Archimedes' parabolic area formula. But actually, it's not really true. What we've just done is proven it in a special case. The special case when the parabola is oriented nicely so that its axis is vertical. So that it's given as a function, essentially, y equals f of x, a quadratic function of x. But to really prove Archimedes' formula, we have to be able to deal with a general parabola in the plane. This is something that makes classical calculus courses a little bit nervous because once you have a parabola that's tilted like this, it's no longer necessarily represented so easily by a nice function. And so the usual techniques don't apply so easily. But our technology deals with this very easily because we are basically orienting things towards curves to begin with. That's really the central orientation. So we can take a general quadratic polynomially parametrized curve, or in other words, a general DCB quadratic curve, which now has a quadratic expression in alpha as its first coordinate and a quadratic expression in alpha as its second coordinate. So we'll write a0 plus a1 alpha plus a2 alpha squared for that x-coordinate, and b0 plus b1 alpha plus b2 alpha squared as the y-coordinate, as in the previous case. So this covers the previous case. That would just be when A0 and A2 are 0 and A1 is 1. Okay, so now one can make a calculation that's exactly parallel to what we just did, except it's slightly more complicated because the two ingredients here are a little bit more complicated, but still not too hard. And you can determine that the signed slice area from u to t of gamma is 1/6 of a1b2 minus a2b1. It's like a cross product term there, okay, times u minus t cubed. So this is a generalization of the formula that we got in the previous slides. And then it turns out that the inscribed triangle, how do you get at that? Well, you have to find out where the point at infinity is on this curve. Right? That plays an important role. It's no longer directly up. That's going to be in the direction a2, b2 to 0. Sort of when alpha is big, these two terms dominate. And then you could take the midpoint of the segment AB, or the side AB, and form that line, and then you can calculate that point C. And pleasantly, that point C is then, it's gamma of V, where V is t plus u over 2. So it's associated with the parameter, which is just the average of the parameters of A and B. And so they can make a calculation just like what we've done and find that the signed area of ACB, this inscribed triangle, is 1/8 of, again, the same quantity A1B2 minus A2B1 times u minus t cubed. And so this thing here is still 4/3 this one. And so we've demonstrated that Archimedes' parabolic area formula still works in the more general parabolic setting. Okay, so now it's time to introduce the other kind of area that we are interested in. Not a slice now, but a cap. So this is sort of on the complementary side, the same way that an inscribed polygon for a curve and a circumscribed polygon for a curve are kind of opposites. So it's exactly the analogous thing. So for a polynomially parametrized curve gamma, as before, we now introduce the signed cap area of gamma from t to u. And it is given by this formula here. So what it geometrically amounts to is, here's our curve, gamma, okay, and there's a point A, which is gamma of t, there's point B, which is gamma of u. There's a tangent at A, and there's a tangent at B, and they meet at this external point X. And we're interested in the region bounded by the curve, but also these segments, the segment AX and the segment XB. So we know what the signed areas of each one of those three things are, so we're just going to use those three ingredients to define the signed area of the cap. So the signed cap area, which is SC from t to u of gamma, or SC of the segment gamma from t to u, is by definition, let's make this a definition, it's the signed area of AX, that oriented edge, plus the signed area of XB, that oriented edge, minus the signed area from t to u of gamma. So minus this signed area here. In other words, we're actually going from here to here. So we could rewrite this if we wanted to as a signed area from u to t of gamma. But I just prefer to do it like this because we're already familiar with that kind of thing here. So we orient things in such a way, and it's just a convention, so that in this kind of situation, both the slice area and the cap area are both positive. And in fact, if we add them, we will just get the signed area of this triangle formed by A, X, and B. Okay, so here A is gamma of t, B is gamma of u as before, and X is the meet of the tangents to gamma at A and B. Now this meet of tangents may not exist. Perhaps these two tangents are parallel. Okay, if that happens, then we'll not say that this thing is defined. It's just not defined. And we might refer to X as the external point of this side AB, sort of associated to this chord, external point of that chord. Okay, so we want to have a look at this situation for the general de Casteljau Bezier quadratic curve. So already what we've looked at is gamma here, which is a0 plus a1 alpha plus a2 alpha squared, and b0 plus b1 alpha plus b2 alpha squared. Now to make our analysis simpler, let's introduce these numbers, delta ij. So that's by definition ai times bj minus ajbi, like a cross product expression involving pairs of these coefficients, where I and j are between 0 and 2, and I is, say, less than j. Now, these quadratic de Casteljau Bezier curves expressed this way, they're parametric curves, they're polynomially parametrized. But they also can be expressed as algebraic curves, and as an algebraic curve, gamma has the following equation in terms of x and y. It's a quadratic equation in x and y, and maybe it looks a little bit interesting. It has a lot of these deltas. So here's delta 0, 2 squared minus delta 0, 1 times delta 1, 2 plus delta 1, 2 times the quantity b1x minus a1y minus 2 delta 0, 2 times b2x minus a2y plus b2x minus a2y all squared equals 0. Okay. So that's kind of interesting because this is a general quadratic polynomially parametrized curve, or DCB curve. These are important general family of curves that we can sort of deal with from the calculus point of view, and they're the quadratic ones. So it's nice to be able to immediately write down an equation that they satisfy, an algebraic equation. Okay, so we're interested in analyzing such a curve. We're assuming we have 2 points, A and B. A is gamma of t and B is gamma of u as before. And then we can determine the equations of the tangents to those curves because we know how to do that. And then we can find the meets of those tangents. That'll be the point x. And when we do that, here is what we get. So x turns out to be, it's a lot like this, but it's a0 plus a1 times the average, t plus u over 2, plus a2 times the product, tu. And here, correspondingly, b0 plus b1 times the average plus b2 times the product. So that's a nice formula for the external point associated to a pair of points on a general parabola in the plane. These things are always parabolas. All right, so we have exact expressions for the point A, the point B, and the point X. So now it's straightforward for us to calculate the signed area of the oriented edge AX. That turns out to be this expression. 1/4 times u minus t times this expression in t, delta 0, 1 plus 2 delta 0, 2 times t plus delta 1, 2 times t squared. And correspondingly, the signed area of the oriented edge xb turns out to be something similar with u's instead of t's. And the signed area of the curve itself from t to u, well, that again is another expression. It's delta 0, 1 over 2 times u minus t plus delta 0, 2 over 2 times u squared minus t squared plus delta 1, 2 over 6 times u cubed minus t cubed. So these are all straightforward calculations, for example, just using the fundamental theorem there. Okay, so now these are exactly the ingredients we need to calculate the signed cap area of this quadratic DCB curve from A to B. In other words, this black region here formed by these two tangents and the curve itself. We're talking about this region right here. Okay, so the signed cap area is the signed area of AX plus the signed area of XB minus the signed area from T to U of gamma. In other words, minus this signed area determined by the segment itself. Okay, so we have to take this expression, we have to add this expression, we have to subtract this expression, and we have to simplify. Okay, very pleasantly, what we get is this relatively simple expression. Delta 1, 2 over 12 times u minus t all cubed. And this delta 1, 2 is a1b2 minus a2b1. It's the same factor that appeared in the signed sliced area of the same thing. In fact, this is related to that because that previous one had a 6 in it. So this is exactly 1/2 the signed slice area of that same segment. What that is telling us is that the signed slice area, that was what you get when you take the curved segment and you slice it with this green line here. So it's that green area there. And we're saying that the black area is always exactly 1/2 the green area. The circumscribed region is 1/2 of the inscribed region, roughly. Archimedes tells us that this thing is 4/3 the signed area of ACB. Here's the point C. Maybe I should put that in there. That's the same point that we were using when we were talking about Archimedes' original theorem. So we have this inscribed triangle ACB, and we know that the signed slice area is 4/3 the area of that inscribed triangle. So this quantity here is 4/3 of this, and so 1/2 of this will be 2/3 of this. So that's telling us that the signed cap area is 2/3 of the signed area of ACB. So if we know this, this triangle area here, okay, then by multiplying it by 4/3 we get the sliced area, and by multiplying it by 2/3 we get the cap area. And the cap area is 1/2 of the slice area. Now, these are very beautiful things. I don't think this one here is actually in Archimedes, but I mean classical geometers would have been very familiar with this. But here we have nice proofs, just relying on our technology for the algebraic calculus and showing that we can extend. We can extend Archimedes to this more general setting. We can obtain some new information, and we can also bring into question, what happens for higher degree curves? Does something similar happen? That's a very interesting question. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.